Good morning. Good morning to everybody, and welcome to the morning webinar session of today. This is the second of the two lessons about the fundamental of the surface EMG signal processing by means of the BTS EMG analyzer application. This is what you saw during the first lesson. If you remember, we started with a quick review about the surface EMG. We talk about some common signal processing tool useful to extract amplitude information from the signal. This can be useful, for example, to understand for how much a muscle is active or if one muscle is more or less active in one condition respect to another condition, for example, and so on. In particular, we talk about the full wave rectification algorithm and about how to extract the main shape or the envelope from the EMG signal by means of the root mean square algorithm or by means of the integrated EMG. And then we learn about how to compute typical parameters as the mean, the peak, or the IRV, for example. Then we had a look about how to perform the average of more than one trials, which require the normalization of the signal respect to the time domain. Finally, we talk about amplitude normalization of the signal level that is useful for data comparison. During the lesson of today, we will conclude the topic about the amplitude normalization by talking about the signal amplitude normalization respect to a reference activity value. Then I will introduce you to the main concept about the frequency analysis of a signal and about signal filtering. In particular, we will talk about high-pass or low-pass filtering. Then we will have an example about how to extract onset-offset timing information from the muscle activity, and then we will conclude with an easy example about how to use frequency analysis to investigate about muscle fatigue. Well, you should remember from the first lesson that different criteria can be used to perform amplitude normalization of the signal. The internal peak value can be considered as a reference value, for example. Otherwise, one more stable criterion that is suggested to be used could be to use, instead of the peak, the mean value as a reference. This is what we covered during the first lesson. I would like to conclude about that now with another widely used criterion for the amplitude normalization, that is the normalization respect to the maximum voluntary contraction value. Remember that amplitude normalization is a useful tool for data comparison about the amplitude of the signal. The how much question cannot be answered by the original microwatt scaling amplitude. But in that case, a rescaling to % of a certain reference value has to be applied, for example, respect to the maximum voluntary contraction. The question how much EMG basically addresses to the interest to understand how much work or effort a certain muscle has to share in certain exercises of task. This is important to understand the effect of treatment and training exercises, for example. Imagine that during a training with a leg extension machine, for example, you want to understand if a slow or fast movement is better to be executed by the athlete. So you can compare, for example, the level of activity in the two different situations in order to understand the amount of muscle used in those conditions. During an MVC test, we record the EMG signal while the subject is performing a task which requires a strong effort from the desired muscle. Typically, during that test, the muscle has to resist against a static fixed load, acting into the opposite direction. So the maximum voluntary contraction are performed against static resistance, and normally they are isometric contractions. During the maximum voluntary contraction, the amplitude of the related EMG activity, for example, we consider the rectify and the smooth EMG, and you should now know how to compute that, is measured, and so this activity is measured and then used as a target for the other voluntary contraction of the same muscle. The maximum voluntary contraction test has to be performed for each analyzed muscle separately. To perform this kind of test, Some exercises can be arranged using belts in combination with manual resistance, for example, and also standard training machines can be very helpful to do that. You can use a repetition of maximum voluntary contraction, which lasts for a few seconds and then relax and then start again and so on, or you can use a single longer voluntary contraction. Logically, patient cannot perform maximum voluntary contraction test with injured joint, and so in that case, other criteria has to be considered to perform amplitude normalization. Consider that in general, it is not really important to have the maximum activity, but just to have a test that can be performed in the same way in different times, and that can be used as a reference for reliable data comparison. So now I want to show you a quick, easy example about how you can compute the amplitude normalization of a specific signal respect to the computed MFC value by means of our EMG analyzer application. So let me show this in this example. We have collected a series of maximum voluntary contraction repetition. Okay, so now we are going to compute the maximum voluntary contraction value that will be considered as reference value for the normalization of the second test, where the subject has performed the execution, for example, with the load. So the first thing is to compute the envelope of the signal. So we are going to use a root mean square algorithm with a duration of 500 of milliseconds. You should remember from the first lesson how to compute that. So, okay, so now I'm going to define the time window, duration, 500 of milliseconds. Okay, and so that is the result. So now I will consider as MVC value the peak value, but not exactly the peak value. I want to use the average value of the signal around the a portion of the signal around a time duration of 1 second. So I will consider the peak. So now I'm considering the global peak, and I will compute the average around plus 500 milliseconds minus 500 milliseconds, so time duration of 1 second. Okay, so now I'm defining the duration of the period in which to compute the average value for the root mean square. Okay, so now I'm defining the two temporal events. So the peak time minus 500 of milliseconds. And now the second will be T2 as the peak time value plus 500 of milliseconds. So we are going to consider a period of 1 second around the position of the peak. And now I'm going to compute the average value in this period. So use mean between two events, mean value between two events. Okay. So remember that not to use exactly the peak, but to consider this algorithm, so to consider the mean value around a portion duration of 1 second, it can give you a more stable reference value for the maximum voluntary contraction. Okay, so now I'm going to compute the root mean square for the signal where we have executed the test. So this is the second. Okay, so you should already remember how to perform that from the first lesson again. And so now we can normalize the amplitude of this signal activity respect to the computed MVC value. So we are just dividing the root mean square amplitude value respect to the reference. Okay, so the first input will be the root mean square EMG for the first condition. We are dividing respect the maximum voluntary contraction value, and the same we can do for the second signal. Okay, so this is the first. So now, as you can see, we have on the y-axis a percentage of value respect to the value of the maximum voluntary contraction. So, for example, you can see that on the first exercise, we don't reach the maximum value. So the amplitude value are below 100%. That means that we don't reach the maximum voluntary contraction value. While on the second exercise, we go above that value in some contraction. So this is just a quick example about how you can perform a computation like that by means of the EMG analyzer application. Well, the second topic I want to introduce you is about the analysis of the EMG signal into the frequency domain. And so the first main concept that we have to discuss about is what is a signal spectrum. I don't want to go into details about the mathematical algorithm used to perform that now, but I would like just to let you more easily understand what it represents and how to use it. As you know, we can divide the visible light, white light, into different colors. And to describe the map of the color, we can graphically display the contribution of each color to the total amount of light. The same can be for the voice or for the music, for example, that is composed of different sounds. Let me give you another example. For example, a pure tone as it is the note A, for example, can be characterized by a well-specific frequency and amplitude value, and can be represented into the time domain by a sine wave of amplitude A and period T. The same information can be represented into the frequency domain as a single vertical spike of amplitude A at the frequency F of the tone. So for sounds in general, we can say that it can be broken up into the sine wave that have different frequency and amplitude. These sine waves can be played at the same time to recreate the original sound later. The graph, which represents on the x-axis the frequency values and on the y-axis the amplitude value, is called the spectrum of the signal. And this is a useful tool to describe the amplitude contribution of the different frequencies which compose a complex signal. Exactly is the same for the EMG signal, that is composed by the superimposition of the different electrical signal coming from the different muscle motor units in the same time. To investigate about the surface EMG signal, it's typical to perform a frequency domain analysis also. So, for example, the discrete Fourier transform or the Welch method are common algorithms widely used to compute the EMG spectrum or the power density spectrum. The FFT is computed on the global time, and this is the results of the spectrum, while the power density spectrum considers the spectrum on a time epoch and then average the values. In this way, we can convert the sample function from its original time domain to the frequency domain. This is a typical spectrum coming from a surface sEMG signal. It starts around 10 Hz. The peak frequency is around 80 Hz. And from here, the spectrum curve decreases and reaches almost zero between 200 or 250 Hz. Note that the more significant part of the spectrum is between 30 and 250 Hz. So now I want to show you how you can compute the spectrum by means of our EMG analyzer application. So this is a signal, an example. So imagine that now we can compute the spectrum. We have specific block into the application to compute that. So you can choose between the DFT or the periodogram of Welch. That is the discrete Fourier transformation, the first. So you have just to drag and drop the input, so the raw EMG, to get into this block to get the spectrum. The second option is for compute the power density spectrum. So in this case, you have to put as two input instead of one. The first has to be the raw signal, and the second, the duration of the time epoch. So we will use 500 of milliseconds. So the signal, and this is the results. Okay, so now you should have learned about how you can compute the spectrum of the signal by means of our application. Okay. In general, I would say that the frequency analysis is a good tool that can be used to check about the signal quality, and that can be used to investigate about undesired noise or signal artifacts. For example, in these slides, you can see two typical examples. On the first image, you have an example about a typical spectrum containing 10 Hz moving artifact. So you can see that the spectrum is shifted on the low frequency. While on the second image, you have a typical spectrum containing a very huge power line noise set at 50 Hz. Those undesired noises can be eliminated or reduced by means of specific tool called filter. So what are the filter? A filter, we can say that a filter is a tool designed to attenuate specific ranges of frequency while allowing others to pass. So the stop band of a filter is the frequency range which are attenuated. The pass band of a filter is the frequency range which is transmitted. So what is an high-pass filter? By applying a filter like that, all frequency below the cutoff frequency of the filter will be attenuated to zero. So the frequency below. What we call FC is the cutoff frequency of the filter. Let's now show you how to perform an high-pass filter to a signal by means of our application. So in this example, I have voluntarily created some low-frequency artifact noise, which are the one I'm showing on this graph. So now I want you to show the results of a power density spectrum of a signal containing a very huge amount of artifacts like those. Okay, so now I'm defining the time duration of the epoch to compute the spectrum. Again, 500 of milliseconds. This is the signal that I want to use. So as you can see from this spectrum, we have a very, very big amount of contribution coming from the low frequency moving artifact. So now I want to show you how you can filter a signal like this to remove the low frequency moving artifact. So I'm going to use, for example, a Butterworth high pass filter algorithm. The first thing that you have to do is to define the cutoff frequency. So you have to define an input, fixed input. I'm going to choose 30 Hertz, for example. Okay, and the signal has to be the first input. So now I'm going to show you the results of the filtered signal. As you can see, we have now reduced the amount of the artifacts. And if you look at again the results coming from the spectrum of the filtered EMG signal, you can see that now we have recovered the contribution of the real EMG signal and we have completely removed the artifact. So this is a typical spectrum coming from a good EMG signal. Okay? So this is just to give you an idea about how to use a filter. Another type of filter that can be used is the low-pass filter. In this case, all the frequency higher than the cutoff frequency will be attenuated to 0. Also in this case, we call FC the cutoff frequency. Different filters, it is the same also for the high-pass filter. Different filters are widely used. For example, we can use the Butterworth, the Chebyshev, or the Hemming. So you will find into our application different options between you can choose. They are very similar, but they differ just in the shape in the shape and in the degree of the slope, as you can see from this image. An ideal filter, in fact, has a squared shape, which allow to pass or stop exactly the cutoff respect to the cutoff frequency, while a real filter has not a square shape, but they have different shape and slope. So it doesn't matter now that you know the differences between the different algorithms, but just to know their meaning and how to use it. So what about the low-pass filter? The low-pass filter can be another option to extract the signal envelope, so the signal shape coming from the raw signal. On the first lesson, if you remember, we talked about the root mean square algorithm and the integrated EMG. But also the low-pass filter with a cutoff frequency, for example, set at 10 or 3 Hertz, is a widely used method to extract the shape of the EMG signal and to can compute what is called the envelope of the signal. So now I want to show you an example about how to do that. So this is the signal, and now I'm going to compute the envelope of this signal by means of the application of a low-pass filter. I'm going to use one filter within, so the Butterworth low-pass filter, for example. Okay, remember that you have to type the name of the output. So now I have to define the full wave rectification of the track, because you cannot use the raw signal as the input for the filter. You should remember from the first lesson how to do that and what's the meaning of the rectification algorithm. So the rectified signal will be the input, and then we have to define the cutoff frequency of the filter. It will be a low frequency. So for example, I will start by showing you the results with a 10 Hz cutoff frequency. And this is the results of the envelope. Now I want to show you that the lower the frequency is, the higher is the smoothing effect of the filter. So now I'm going to show you what will be the results of the envelope if we decrease the frequency. So for example, I'm going to use 3 Hz. So again, I'm going to apply a Butterworth low-pass filter set at 3 Hz. Now, again, I have to use as the input the rectified track, and the second has to be the frequency. So as you can see, we get a more smoothing effect on the second envelope respect to the first, because we have used a lower cutoff frequency. Good. So what about now timing information or onset offset information? This type of analysis can be a useful tool to show at what time portion within a specific movement task a muscle is on or off. The main idea of the onset parameter is to compute how long a muscle needs to turn on and how long it stays on. And then we can analyze also how much EMG activity is used within the onset period. So this is, for example, the case of what we want to have during a gauge cycle. The most popular approach to compute the threshold that have to be used compute the standard deviation range of the EMG baseline before a certain activity, or, for example, consider the activity, the average activity, during the resting. Then we will perform a multiplication factor of this range, and then a factor of 2 or 3 will be considered. So when the muscle activity will exceed the defined threshold value, so for example, it will exceed the double or the triple standard deviation range, the muscle will be defined to be on or active, for example. So I'm going to show later a very easy example about how to do that. An alternative solution of this, respect to this, would be to use as a threshold a percentage amount of the local peak activation found within the analysis period. For example, we can use, let me say, the 5% of the activation. Another alternative method would be to define a certain micron level or a certain percentage value respect to the maximum voluntary contraction recording, for example. So now I want to show you an example about how you can do it into the EMG analyzer application. So now we will use this resting trial. So on the first image, you can see the resting activity, muscle activity. So now I'm going to compute the mean value of this activity. So if you remember, we cannot compute a mean value from the raw signal, but we have to consider the root mean, the envelope of the signal. So for example, the root mean square value. And you should already remember how to do that. I'm going to use 300 of milliseconds as a time window to perform the root mean square. Okay, so now we can compute the mean value of the root mean square of the resting EMG activity. Okay, so this is the mean value and the standard deviation. So now I will use a multiplication factor of 3. So 3 is a scalar input that I have to define, and I will multiply the standard deviation value for 3. So I will consider a value of 3 times the standard deviation. And now I'm going to sum this value respect to the mean value of the EMG activity during the resting. And this value will be the threshold value to define the onset offset muscle activation during the activity. Okay, so now we can consider the real activity of the signal, and we are going to define the computation of the onset offset time. To do that, I have to use the envelope of the signal. I'm going to use a Butterworth filter. For example, a low-pass filter. Okay, so now I'm going to perform an high-pass filter before, in order to remove any moving artifact coming that can be present on the signal. It's typical to do that. And now I'm performing a low-pass filter set to 450 Hertz. And now I'm going to compute the envelope. So it is typical to, prior of computing the envelope, to perform a filtering with an high-pass filter to remove the low frequency noise, and then to remove the high frequency with a low-pass filter. Remember that prior to compute the envelope, we have to rectify the track. And now we are going to define the envelope frequency, so 3 Hz, and this is the results. Okay, so now we are going to compare this activity respect to the threshold we have defined from the resting. So now we can identify the events of the onset by choosing this option. So the input will be the envelope and the second will be the threshold. And so now we can ask to the EMG analyzer application to compute automatically the value where the EMG activity is up respect to the reference. We can do the same for the offset value. So again, the input can be the envelope with respect to the threshold. And we can also, in this case, to ask to the application to compute automatically these events. Okay. So also this is a very quick and easy example that you can use to compute the onset and the offset value. So in this case, for example, if we have a cycle, we can define a cycle, and we can say in which is the duration of the activation period of the muscle respect to the entire duration of the cycle, for example. And you should already know how to do, if you remember what we did during the previous lesson. Well, now I'm going to show you some other parameter that can be calculated from the spectrum of a signal. For example, we can compute the mean frequency, that is the mathematical mean value of the spectrum curve. We can compute the total power as the integral, so the area under the spectrum curve, or the median frequency, that is the parameter, so the frequency value that divides the total power of the spectrum into two equal parts. Then we can also compute the peak power value, that is the maximum value of the total power spectrum curve. Within the applied EMG frequency analysis, the most important parameter that can be used, that are normally used, are the mean or the median frequency value. And what we consider normally are their time domain changes during a sustained contraction. This is, for example, widely used in fatigue studies. In fact, within static submaximal contraction, you have that both the amplitude and the frequency-based analysis parameter can show time domain changes during the muscular fatigue. The classical test requires to perform, for example, a constant load level at a well-defined angle position, mass or muscular length, and you can see that due to the recruitment of the motor units, the median frequency of the total power spectrum show a decrease over the contraction time. And this is because the conduction velocity of the motor action potential on the muscle membrane decreases. So this causes the phenomenon of the fatigue, causes a left shift of the total power spectrum towards the lower frequency. So now I'm going to show you an example, but you can consider that the regression coefficient of the median or mean frequency slope towards the lower frequency can be used as a non-invasive fatigue index for the muscle. So now I want to show you an example about how you can compute fatigue indexes from the EMG analyzer application. So on this example, I have voluntarily exaggerated the phenomenon. So now I want to start by computing the spectrum, the power density spectrum of the signal. And I want to show you the shape. So this is the duration of the time window. Okay, and so this is the spectrum, and as you can see, it is shifted with respect to the left, respect to a typical spectrum, if you remember. So now we can, for example, compute the median value, median frequency. And as you can see, it is set around 50 Hertz, so 52 Hertz. So it's lower. The median frequency of this spectrum is lower respect to what you have in a typical unfatigued EMG spectrum. So to compute the fatigue, you have to option into, you have some different option into our EMG analyzer application. The block I'm going to use is specific for the computation of fatigue isometric. So in this case, the first input has to be the raw signal, and then you have to define the signal, the two events which define the signal portion that you want to analyze. So I'm going to define the start and the stop of the time window respect to which I want to analyze the signal. So here we have an isometric contraction. So I want to start from that event, and I want to stop until this. So the start and stop events will be other two input of this block. And then you have to identify the time duration of the epoch that will be considered to perform the computation of the median frequency of the spectrum. So I'm going to use 2 seconds. So let me show you the results. So as you can see, you have a decrease in time of the value of the median frequency value of the signal. Now I want to show you another example where that can be used, for example, if you want to investigate about, oh, I'm sorry, I think that maybe you cannot see the video, but on this case, I want to show you an example where you don't use you don't want to investigate about fatigue during an isometric contraction, but during a repetition of contraction. So in this case, you have other two blocks that can be used to perform the investigation about the fatigue within the EMG analyzer application. I'm going to use this. Okay, so in this, with this block, the first input has to be the raw signal, and the other two input has to be an events. So for example, I'm going to use the peak of the EMG envelope. So we are going to compute the envelope of the signal by means of the same low pass filter. I now set up the cutoff frequency. I'm going to choose 3 Hz. Remember that we have to rectify the signal before filtering. Okay, so this is the envelope. So now I will consider the fatigue around the peak value. So this can be another option. So I have to identify a sequence of events. I will consider the peaks, the sequence of the peaks of the envelope of the signal, so that they will be, for example, this value, this value, this value. Okay, so the second input will be the sequence of the events. And now again, I have to define the duration of the time window for the computation of the median frequency of this power spectrum. So I'm going to use 1 second. And so this is the result. So as you can see, also in this case, we can see a decrease of the median frequency during the different contraction of the muscle. So this is another example about how to use the frequency analysis of an EMG signal to investigate about muscle fatigue. Okay, so, well, I think that we can stop for this, this lesson. During these 2 lessons, now you have learned about the main algorithm the more common algorithms that are commonly used in EMG for the EMG application. So now you should be able to use that within our EMG analyzer application, and I think that you can start to develop your own protocol. So I think I'd like to thank you for your kind attention, and we will see you on another webinar lesson. Bye. Bye-bye.